Okay, welcome back, everybody. So we're in the last two lectures of the course. Now the top lectures, and as I mentioned, there's going to be a guest lecture coming up on Monday, which was very, very popular last year. People really, really liked it. I think that the speaker has brought in actually little sound files of what different animals sound like underwater and how the sound travels and all sorts of different things like that. So it's very, very interesting stuff. I learned a lot. Okay, so last time we had Audrey Parnell talk about climate modeling, and so I'm not summarizing that there because her talk is her own research that I'm not really capable of summarizing without looking at it carefully. But so the class before that, we talked about climate modeling. And that was sort of a precursor to Audrey's lecture. And we also talked about geoengineering. So just as a reminder, geoengineering is this idea, it's a general idea, that we, due to the threat of climate change, the number one thing that everybody believes is appropriate to do, well, the majority of people, is reducing carbon emissions, reducing the greenhouse effect, and that will slow climate warming. But it doesn't actually, when you stop driving cars or whatever, or gas vehicles, you reduce the amount of CO2 you emit, but you don't actually remove the CO2 that is already in the atmosphere. So you don't actually make it cooler, you just slow the warming. And so the question arises, what if we emitted so much greenhouse gases or other things change, like perhaps we've had melting of ice sheets or whatever, and the climate gets too warm, well, maybe reducing emissions is no longer enough because the temperature has just risen and we need a way to cool the climate. And so this is where geoengineering comes in. It's a highly, highly controversial idea, and it's never really been seriously considered at the planetary global scale. But the idea is that we could do something actively, rather than just sort of try to do no harm and reduce our emissions and stop hurting the environment, to do something actively to try to correct the temperature. And of course, it's kind of like a medical intervention when somebody has a disease, right? And there could be side effects. And so understanding what those side effects are is crucial. And what we learn in science is that usually your hypothesis and what you think will happen is only part of the picture. And then there were many sort of unknown unknowns or ideas that you didn't even think of in advance that could become problems. And so that's one of the reasons that geoengineering is highly controversial. And I don't know of anyone in my professional life who seriously believes that it should be implemented now. It's just, on the other hand, many people believe that given the sort of political intractability of the climate problem, it's good research to have in our pocket just in case someday we have a climate emergency and we may need to do something like this. So I mentioned one idea we didn't talk about in detail, but one idea of geoengineering is to put up I think sulfur aluminum particles in the atmosphere that act like little mirrors and reflect the sun away. We're going to talk about actually later on exactly how that would sort of play into the mathematical argument that sets the Earth's climate. But the other one that we talked about is based on biological mechanisms. This is called iron fertilization. So one mechanism that helps to regulate the amount of CO2 that's in the atmosphere is this thing called the biological pump. And so that's shown up here in the upper right-hand diagram. And there's all sorts of details here that don't really, I mean, they're very important if you study marine biology. It all fits together. But from a physics perspective, the key idea is that you have CO2 in the atmosphere. And because we're constantly pumping CO2 in there, the atmospheric concentration of CO2 is relatively high, so much higher than it was in pre-industrial times. And so some of that CO2 gets taken into the surface ocean. So the water has some ability to dissolve CO2 in it. And so the surface ocean just draws down some of that CO2. But if it just stays in the surface ocean, it can actually outgas and go back out into the atmosphere. And then that didn't really help us in the end. So what we want to do to mitigate climate change is to get that carbon from the surface ocean and put it buried down somewhere in the ground where it can't get back into the atmosphere. And biology actually does this naturally. So what happens is, if high atmospheric CO2 concentrations that gets absorbed by the surface ocean, and then there's organisms there in the surface ocean, very, very abundant, because there's lots of light there, lots of nutrients. And those guys do photosynthesis, and then that photosynthesis converts the carbon dioxide into the materials that those cells need, and also oxygen. And then when those cells die, they can sink down to the bottom and basically become sort of part of the seafloor. And over very, very long geological timescales, the seafloor shifts and gets recycled, and over many millions of years, all the atmosphere, ocean, and geology, it's all coupled together. But on the timescales of hundreds of years, that carbon is effectively gone. So it's out of the atmosphere, it's in the bottom of the ocean, can't hurt us anymore. So that's called the biological pump. Before this pump to operate, you need to have photosynthesis. And so it turns out that we're not kind of at our capacity for how much surface ocean photosynthesis and biological pumping we can be doing because of this concept of high nutrient, low chlorophyll regions, which are called HNLC. And so for photosynthesis to take place, the organisms need to have all the things they need for life. And so there are macronutrients like phosphate and nitrogen that are very important. But there are also micronutrients. So these are things that they're called micronutrients not because the nutrients themselves are smaller, it's because the amount that is needed is smaller. But so something like iron is a small but important component of the function of these cells that are doing the photosynthesis. And there are regions of the ocean where there's lots of the other nutrients. So there's lots of nitrogen and phosphate, but it's low in something like iron. And so even though you kind of have an abundance, it's like you have an abundance of oxygen, so that's good for people, but you don't have any food, so they still can't live there, right? So without the iron, they can't do their photosynthesis. And so the idea was, if there's these wide swaths of the ocean where they're iron limited, could we enhance the biological pump by just putting iron in by hand? Just taking iron, breaking it up into dust particles, dumping them into the ocean. Could you do that? And that's been tried. And this is a cool satellite photo of chlorophyll, where here's near Alaska. There's Anchorage is up here. And the color is showing chlorophyll. The reason there's all this black stuff is because this was done in a fairly short time scale. These are clouds. So that underneath these black parts, we don't have any data because the satellite was blocked by clouds. When you look at other satellite data sets, you don't see quite as much cloud cover. That's because in other satellite products you usually look at, they're averaged over multiple days. And so like on a different day, these clouds won't be in the exact same position, right? So as the clouds move around, you kind of see below where the clouds were yesterday and kind of average it all together and get some pressure. So anyway, so this was done, and you can see this little red spot here. That's the fertilization experiment location. So they dumped a bunch of iron in here, and you can see there's a very, very obvious bullseye of enhanced surface chlorophyll right there, which shows the idea that if you do this, if you fertilize the ocean with iron, you can enhance the biological pump, and then you can draw down extra CO2. However, generally this is not considered to be a good idea to do on any large scale because of multiple reasons that had to do with ecosystems. So essentially, when you do this, you can actually cause harmful types of phytoplankton to form, and also you can deplete these background levels of nitrogen and phosphate, and also I think you can cause anoxia, although I can't remember how that happens. So it's considered very dangerous for the ecosystem. You can have long-term effects that are negative. However, the idea does work. You can draw down carbon doing this. Okay, and the second topic was climate modeling. And there were a couple of key ideas about how does the climate model actually work. So it obviously it's some kind of computer program that's going to predict what the climate is like in the future. And in many ways, climate models are actually very, very similar to, and they're an outgrowth of, numerical weather prediction. So one of the first sort of big achievements in computers was when computers first became practical. And this was, I think, during the Second World War. They just said, what if we just took physics equations for the atmosphere, put them on the computer, and we use that to predict the weather? After a while, that was successful. And then the same idea is done for climate models, except for instead of just the atmosphere, you also have the ocean, ice sheets, et cetera, lots more physics. And so a couple of the principles are, the computer can only deal with a finite amount of data at one time. So you can't have, so really the climate system is continuous. we say like how many points in space are in this room, right? It's an infinite amount, unless you start talking about individual atoms and things like that. And so you can't handle an infinite amount of data in any spreadsheet. The spreadsheet would be infinitely long. So what we have to do is make it finite. That's called discretization. And so we basically take the atmosphere and the ocean and the ice sheets and break them up into these little cubes, and you consider sort of the physics of it cube by cube. And so each cube has like a force law. So the force on the cube is related to the acceleration or whatever. And then we break the climate up into submodels. We have an atmosphere model, ice model, ocean model, maybe land surface vegetation, that kind of thing. And then the models are coupled together. So for example, the atmosphere component of the model and the ocean component, they exchange energy, and this is through the mathematical equations. But the way they exchange energy depends on the state of the two models. So for example, if there's sea ice, then that acts as a insulator, and that reduces the heat transport between the ocean and the atmosphere. And if there's no sea ice, then you have more heat flow. So the models are coupled together in a lot of different ways. And then the last there's two more major topics we talked about. So one is like how big do these grid boxes have to be? So one idea would be we want those grid boxes to be small enough that we can capture all the physics basically. So from the small, from the size of like I say, a raindrop all the way up to the size of a hurricane. If you try to do that, the amount of data in terms of like RAM memory that you would have to have in your computer program is some astronomical number, like 10 to the 20 terabytes. So not only can we not do that now, in no conceivable near-term future of the next few hundred years could we ever get anywhere close to doing that. So we have to have our boxes have to be pretty big. We can't have a box the size of a raindrop. That leads to too many boxes, too much memory that's necessary. But if we make the boxes, say, a few kilometers across, then we actually can do it. But then what do we do about the fact that we know physically there's raindrops and smaller scale vortices and different things happening inside those grid boxes? And so that's the idea of parameterizations. So what a parameterization is it's a sort of made up approximate formula that some person devises based on their own physical reasoning or maybe looking at data or whatever. And this is an example of a very complicated, I show this example because it's so shockingly complex looking. But this is one of the more complicated type of parameterizations. But this one's called cloud microphysics. And so in clouds, there's all sorts of stuff happening. So like you have water droplets condensing. But they don't just condense out of nowhere, they tend to condense onto what are called cloud condensation nuclei. So you have like a little piece of dust floating around the atmosphere, and then the water condenses as a little droplet with that piece of dust inside. And then when you have a raindrop that's falling through the cloud, it can pick up other raindrops as it drops and grow in size, for example. You can also have phase transformations. You know, ice and snow and water, and there's different types of ice. So graupel here is a kind of hail. And so all of that stuff to answer like basic questions like, is the temperature going to warm when we emit more CO2? You do not need this kind of complicated parameterization. But to answer some types of questions, you do need these types of complex ideas having to do with what's going on in the inside of clouds. And so climate models are full of these. So for every process that's too small to be properly modeled with, say, a few kilometers in between your grid points, we have some kind of made-up formula. And those are tested and challenged and improved over time. But the basis of the climate model is essentially you take your discretization, then you put the laws of fluid mechanics on this discretization, and then in between the grid points you put stuff like this to model all the smaller scale stuff. And then the last thing we talked about was the butterfly effect and how chaos, much like in the Lorentz equations, also operates in climate models, sometimes to a shocking degree. Okay, so that was a bit of a long intro. So today, so the thing about climate models. So the way that climate models are used, why do we have them at all? The reason is that we want to know how is the climate going to warm as we continue to emit greenhouse gases. So something that's very, very typically done is that you will take the climate model computer code and you'll say, all right, I'm just going to put in by hand that the CO2 is going to go up. Maybe people might double the CO2, or they might put in an estimate of if we continue our normal energy systems, how much more CO2 will we add to the climate system over time. And then they use all these equations and parameterizations and discretizations and everything to compute how much is the temperature going to go up overall, and then also regionally. So when you think about how this whole thing is done, it becomes a little bit suspicious because there's all kinds of these formulas and sort of approximations that are inside these climate models. And these approximations, they're called parameterizations. And one of the reasons that they're called parameterizations is that they are filled with parameters. And so a parameter is just a number that describes how strong something is. So like, for example, on this diagram, there's all these little arrows. So, so cloud ice can go to water vapor. Or, what's another good one here? Rain can go to precipitation fallout. So that's pretty simple. You have rain, you have water droplets in the cloud, and that can cause precipitation. But exactly how much rain do you get when you have a certain amount of water droplets or whatever, right? And the answer to that question is difficult to know for sure. And so people just kind of put a number on it, and that's called the parameter. And that's based on looking at the literature, maybe studying clouds in experimental cloud chambers or whatever, yes?
How do you add chaos to these parameterizations?
How do you add chaos?
Yeah,
so let me return to that just in a minute. That's a good question. So in practice, how are these parameters set? How do we choose the values? What is done is that you have a computer code that predicts climate, and then you just run it, and you ask, what does it predict for today's value of CO2? What should the climate look like? So not looking at warming or climates of the past or anything like that, just put in the atmospheric greenhouse gas concentrations that we have today, and what does it predict for things like surface temperature distribution? And if we want to use these models to predict future climate, it stands to reason that we had better get today's climate correct, right? Otherwise, our model's kind of junk, right? We don't know, it's just, maybe it's some interesting mathematical equations, but it doesn't actually pertain to the climate. So what is done is called tuning. So we have all these parameterizations, and there's all these numbers in there. And what people do is they subtly adjust those numbers within reasonable ranges that are considered reasonable based on physical ideas, until the climate gets to a climate that looks like today's climate. So you tune the parameters of the model, you adjust them, until such a point as you get a reasonable climate out that looks like today's climate. If that sounds a little bit shady, it 100% is, although I don't know of a better way to do it. But the question arises. So suppose we take all of our parameterizations and we we tune the parameters, we get a pretty good climate. Maybe we get exactly right for the climate of today. Let's say our model's very, very good, so we get the exactly right climate today. Now we double the CO2, or CO2 is increasing, and now the climate's going to warm. Do all the parameters in this, in a warmer climate, does the rate of conversion from cloud water to rain to graupel to snow, do all of those things stay exactly the same when you change the temperature? The answer is no one has any idea. And in general, it's a major concern to ask, if we tune a climate model for today's climate, and then we change the climate and ask how the future is going to look, do all of those parameterizations and tuning, does that hold up? Or are those going to be wrong now for the future climate? And basically, even though we might predict today's climate right, is that going to be accurate for the future climate? There's actually a very famous problem here called the problem of compensating errors. So when you do all these tunings, you might have two parameters, one that makes it warmer and one that makes it colder, right? And you can adjust those to both wrong values. But if you have the one that makes it warmer at the right value and the one that makes it colder at the right value, those two things can compensate, and you might get the correct temperature, even though both pieces of the physics are wrong, compensating errors. So if you have compensating errors in your model, then when you change the situation, maybe those errors won't compensate anymore, and you're just going to get some unreliable prediction out. So I don't want to sound too negative about climate modeling. It's very, very important, and very smart, hardworking people work on it, and we've made a ton of progress, and things are constantly peer-reviewed and challenged, and et cetera. I do this kind of thing myself. But you have to be very realistic about the fact that you're working with models that are, it's not reality, and a lot of assumptions and potential pitfalls are involved in that kind of work. Okay, so given that context, what can we do to try to improve our understanding of whether or not our climate models are reliable? The challenge with this, and this is where we're getting towards climates of other planets, and we're going to talk about paleoclimate on Mondays, or Wednesday. So a challenge with climate, as I mentioned before, is that we only have one climate at any given time. So climate changes over time, and we can look at those changes. But if we want to know how good is our model, can we predict today's climate correct? We can't really do a controlled experiment like you would do in a chemistry lab or a physics lab, where you change, like, you have a pendulum and you change the length of the pendulum, you change the mass, you look at how it responds, and you can do a controlled experiment and test the theory in a lot of detail. That's not possible because we only have one Earth, obviously. So what can we do? Are we stuck with basically one model and one data point, or can we do better than that? And it turns out it's challenging to do better, but we can do somewhat better. And that's the topic of today's discussion, which is climates of other planets. So in principle, when we just talk about physics, one of the underlying assumptions of physics, in general, is that the laws of physics are the same everywhere. So if we worked out physical laws on Earth, like gravity, chemical equations, whatever, if those same circumstances were to arise on the moon or Jupiter or anywhere else, then we should get the same stuff happening, that the physical laws don't depend on where you are in space. It's a fundamental assumption. It's not really possible to test that other than with cosmology, but that's what we all believe. And so one thing we could do is take our climate models and ask, if we use them to model other planets, at least that would give us a few other data points. We could check our model. And so that's one thing we can do, is look at climates of other planets and see if the modeling works well for those. And then the other example, which I'll talk about next week, is paleoclimate, going back through the ice core record, sedimentary record, tree rings. There's lots of other ways to get data from what the Earth's climate was in previous times. And then we can try to see, do our models capture that as well? And so these are all different ways that we can bring in extra data to try to validate and test and improve the climate models that we rely on to predict the future of our climate and to understand what kind of interventions we need to do to minimize the damage. Okay, so with 20 minutes left, we'll get into the material. All right, so planetary climates. So this is what I mentioned before, so you can't do experiments. So you can either look at climates of the past, or you can look at climates of other planets. So here I've shown, for example, so here's the Earth from space. If you wanted to look at another planet, so this is Mars. And so Mars looks obviously very different from Earth, so you would expect maybe there's some differences in the climate. And on the bottom, this is a artist's rendition, not a real photo, of a snowball Earth. So we talked about snowball before, and this is an extreme form of an ice age. And obviously in this paleoclimate scenario, when the Earth is covered with ice, the albedo is going to be very different, and you expect, certainly the temperature is going to be a lot colder, for one thing, right? So differences between these different climates, and this provides a framework for testing our understanding. Okay, so I'm just going to open this up for a little bit of a discussion. So in terms of, so climate obviously is made up of numerous factors: precipitation, droughts, and temperature, and everything. But at a very, very gross level, we could say the simplest climate feature that I'm interested in is the overall global surface temperature of the Earth. So what are some of the factors or ideas, physical factors, concepts? What types of factors determine the overall surface temperature of the Earth, say compared to other planets, right? So we know different planets have different temperatures. We'll talk about exactly how different. But what are some of the things that are involved in that? Any ideas? Yeah.
Distance to the sun.
Distance to the sun. So I'll actually I'm gonna talk about this explicitly. But so why does that actually matter?
It's the amount of energy we receive from the sun that that warms up the atmosphere.
Right. And so what's the relationship there, like with the distance and the radiation?
So it's like 4 4 square or something?
It's inverse square.
Inverse square, yeah.
Yeah. So as you get further away, it gets dimmer, right? So as the Earth gets further from the sun, or any planet gets further from the sun, the radiation, I'll talk about this very explicitly with equations and stuff, but the amount of radiation that you receive gets the sun seems dimmer the further it is away, right? That's pretty obvious because when we look up in the night sky, we're not warmed by those distant stars nearly as much as our sun. So distance from the sun, that's one huge factor. Any other ideas? Yeah.
The albedo feedback.
Albedo. So albedo and the feedback. I'm talking in such a simple way that I'm not even going to talk about feedbacks more than a little. But the overall value of the albedo is very important because that tells us of this radiation we're receiving from the sun, how much do we actually keep versus how much is reflected away. Right? And then the feedback effect is if you change the distance from the sun, that would actually change the albedo, and those two things kind of play off of each other, and you get amplified changes. Anything else? There's one other really important factor. There's numerous factors. You can talk all day, but there's one other really important factor. There's three main factors: albedo, Earth-Sun distance, and there's one other one that's really important. Don't have any idea?
Greenhouse effect.
Greenhouse, yeah, the atmosphere. So different planets have different atmospheres, and that, as we'll see, that has an enormous effect on the surface temperature. And there's really spectacular examples of that in our solar system. So these are the three things. So we've got distance from the sun, our albedo. So this is how much radiation we get, what's called at the top of the atmosphere. So before any physics has come in and there's no ocean currents or any wind, we haven't thought about any of that yet. Just at the top of the atmosphere, how many photons per time are we getting in from the sun that carry energy? Then albedo, how much do we reflect those back off to space when they hit off ice or whatever? And then the greenhouse effect, when the atmosphere is trapping heat. And we'll talk a little bit about that at the end if we have time, or maybe on Wednesday. And so all these factors are dynamic. They change over time. The orbit changes relatively least. We talked about that. We call that Milankovitch. There's slight variations in the orbit. But albedo changes a ton. Obviously, we looked at snowball Earth, would have a very high reflectivity. And then greenhouse gases, we're changing them all the time. So here's a table. And this shows the surface temperature of various planets in the solar system, and the moon also. And this is in Kelvin. So to convert this to regular degrees, you got to subtract off 273. So for the Earth, minus 273, that works out to be about 15 degrees. That's the global average surface temperature. That's probably pretty consistent with our experience. Mars is quite a bit colder, about minus 30 or so. Moon, we won't worry about the moon. And then Venus is 730 degrees. So that's basically like almost 500 Celsius on the surface. And so question is, we have certain ideas about how climate is shaped. Can we explain this basic pattern? Or is it true that our ideas can explain what's the difference between these temperatures of planets in our solar system? So actually, Audrey talked about this. So she talked about climate models of different complexity. And so she said there's, what I was mostly talking about when I talked about climate modeling are kind of gold standard, state-of-the-art climate models with all the bells and whistles, called IPCC class, the Intergovernmental Panel on Climate Change. But climate models have a wide range of complexity, and many different types are very useful. The simplest type is called an energy balance climate model. And so in an energy balance model, you're not talking about wind or ocean currents or anything. You're really talking about energy coming in and energy coming out. And the idea is that in equilibrium, those two things must balance. So we observe that CO2 emissions aside, the Earth's temperature is fairly constant, right? It's warming slowly, but it's generally pretty constant. It's not like changing wildly from year to year. And now imagine that the energy that we get from the sun is not being balanced by energy that we emit. I'll talk about why we emit energy, but so the Earth loses energy through some mechanisms, and it gains energy from the sun. And if those two things were not in balance, the Earth would be warming and cooling all the time. We'd see temperature shifts. We don't see that. So we know that the energy that we get in has to be balanced by some kind of energy flux out. And so the energy, that's the principle of energy balance. And sometimes you can write an equation that allows you to actually predict the temperature based on that principle of energy balance. So the idea is that the energy in depends on our distance from sun, also albedo. We can say basically it's a constant energy in. If we ignore Milankovitch, you can include that also. And then the energy out has two real components. One is the reflected radiation, so radiation comes through the atmosphere, bounces off the ice, and goes right up to space. And the other one is called black body radiation. So can you put your hand up if you've heard about black body radiation before? Okay. And so probably this is going to break down largely along physics versus ocean sciences. So black body radiation was discovered, I think in the 20s, maybe the 1910s. And it was one of the first observations that led to the understanding of quantum nature of reality, quantum mechanics. But basically, you can think of it as it's how a thermal camera works. So this is I just Googled this morning. So there's a thermal camera, and this sees heat. You see, if you look closely here, the y-axis you probably can't see is temperature. So the colors represent temperature. And so here's an image from a thermal camera. You can see a person, another person, and our heads tend to be kind of warm, so that's red, and then the clothes are not as hot. Maybe they're, because the outside of the clothes has been cooled by maybe it's a cold day. So different, you see where the skin is exposed, the hands warmer. So this camera can see the heat. So how does it see the heat? How can you see temperature? The reason is that all, and we'll talk about this in a bit more detail, all bodies, all objects that are at a finite temperature, so not 0 Kelvin, but any temperature higher than that, we emit radiation all the time. And we emit more radiation depending on how hot or cold we are. So the warmer you are, the more radiation you emit, and then the colder you are, the less. And so you can see temperature by just having a camera that's calibrated to pick up the special kind of photons that we emit based on this black body radiation principle. So the idea is that in equilibrium, the energy we get in from the sun has to balance the energy going out. So we might have an equation, E in from the sun equals E out. And the key thing is this actually allows us to predict the temperature because of the principle that you emit more black body radiation depending on your temperature. So your outgoing radiation depends on your temperature. Ingoing radiation is constant. So what happens is, imagine you started out cold. You start getting in more radiation from the sun, your temperature warms up, you start emitting black body radiation a little bit. At some point, you're going to get so warm from the solar radiation that your temperature rises to just the point where your emissions now balances what's coming in. And so now your temperature will stop changing. It'll be in equilibrium because now the two things are balanced. And so based on that principle, you can actually solve this equation. You have to make it more explicit first, but you can solve this equation for this t variable, and that's our prediction for the surface temperature. Okay, so looking at the two parts of the equation, we have E in and E out. So E in, as we mentioned, was an inverse square law. So here's the idea. So we have the sun's emitting a certain amount of total energy per time. So it's just spewing out loads and loads of photons, and that has a certain amount of energy in joules per second. So energy per time is coming out. But that energy, it radiates out in all directions. And you can think of it as it gets spread out along these sort of spherical surfaces. So you can kind of track the energy spreading out in a sort of spherically symmetric pattern. And so as time goes on, as those photons radiate out, it's the same number of photons distributed on larger and larger spheres. And so because the surface area of a square, of a sphere, goes like is proportional to the square of the radius, 4 pi r squared, that means that the amount of solar radiation at any particular point, it dims with an inverse square law. So if you have a certain radius, you have a certain amount of solar radiation. If you double the radius, then the radiation goes down by a factor of 4. If you triple, it goes down by a factor of 9. And so in general, as further and further you get away, the solar radiation dies off, and it dies off pretty rapidly, like 1 over the square root of the distance. So you can plug in some numbers. If you know the total radiance of the sun, and you know the Earth-Sun distance, we can work out that at the location of the Earth, the solar flux, so the amount of photons that are coming, is about a little bit more than 1,350 watts per meter squared. So that's joules per second is a watt, and then that's distributed over an area. So it's watts per meter squared. And so how much of that do we catch? So you can think of it as having the Earth is very far away from the sun, so the solar fluxes are kind of coming in like this, like straight, called the plane wave. And the Earth is going to capture an amount that's proportional to the shadow that's left. If you put a screen behind the Earth would block out part of that, right? And so that area is the amount of solar radiation that we absorb. So we know that based on the inverse square law, there's 1361 watts per meter squared. The total amount we absorb is equal to that value multiplied by the cross-sectional area of the Earth. So it's not the surface area, it's the cross-sectional area, which is pi r squared. Then the Earth is rotating, so that total amount of energy gets divided up across the whole Earth's surface. And so the top of atmosphere flux here, F top of atmosphere, is equal to this amount of radiation that's absorbed, which is that number times pi r squared. But then you divide by 4 pi r squared, because we spread that energy over the surface of the Earth. So it turns out the factors of r, they cancel out, and the top of atmosphere flux, so how much radiation per watts per meter squared is coming at the top of the atmosphere, ends up being S naught over 4, where S naught is that 1361. So you may have seen this number before, 340 watts per meter squared. That's the top of the atmosphere radiated flux that we get. Now, when you track for albedo, so some of that's reflected. So turns out that the average albedo, we usually use the symbol alpha, is about 0.3. So that means that we reflect away 30% of the incoming radiation on average, and we keep 70%. And that 30% comes from a sort of a complex average over different types of surfaces. So ocean versus trees versus desert versus ice sheets. And so you're blending together water with no ice or anything on it. You can absorb, depending on the angle actually, more than 90%, and then very reflective ice can be more like 10%. And so it's a highly heterogeneous average, highly localized and regional. But if you average over everything, you get about 30%. And so we keep 70%, so we take our flux multiplied by 70%, which is 1 minus the 0.3, and we get about 240 watts per meter squared, which actually comes in. Okay, so I'll just do this as the last slide, and then we'll pick this back up on Wednesday. So what's the energy out? So this is another thermal image. And so you can see, so these are 2 cups of coffee. One you have let it sit for a while and cools down, and the other one is fresh. So the hot one, bright red, this means it's emitting tons and tons of photons. And the cool one is emitting relatively little. So why does this happen? And this is the last topic I'll mention today. All matter, this chair, your body, whatever, is made out of charged particles. So we're electrically neutral, meaning we have no overall charge, but that's because we have lots and lots of charged particles, like protons and electrons, but they are in equal numbers, so the charges cancel out on average. However, if you look inside a crystal, this is meant to be a crystal. So if you think about a crystal structure, you usually have these lines would be straight, right? We would have straight crystalline lines. But because of thermal energy, the particles that are making up this crystal, they're jiggling around all the time. They have some energy, they're not staying still. And so it turns out that when you take a charged particle, these particles are charged, the nuclei at least, when you have them accelerating, so anything that's jiggling around is accelerating because its velocity is changing. And accelerating charges, the laws of electromagnetism tell us, emit electromagnetic waves. And this is how an antenna works. So if you have a radio broadcast antenna, there's this long conductor thing, and you send these currents up and down this antenna, and the charges move back and forth and accelerate, and that sends out radio waves, for example. So the same thing is true in any material that's at finite temperature. It turns out if you're at 0 Kelvin, these things don't move at all. That's the definition of 0 Kelvin, absolute 0. But if you're at any finite temperature, these things jiggle around, and when they jiggle, it's kind of like each of them is kind of like a little miniature antenna. They fling off these waves. And the higher the temperature, the more they jiggle around, and the more waves they fling off. And so it turns out that there's a very simple formula that comes from quantum mechanics for how this actually works. It's called the Stefan-Boltzmann law, and the next class will actually determine we'll show how to use this to calculate a specific prediction for the surface temperature of the Earth. And it says that the amount of radiation we emit, and this is watts or joules per second per surface area. So you emit from your surface. So the more area you have, the more photons you emit also. And so that flux of photons per surface area is equal to sigma, which is a constant called the Stefan-Boltzmann constant, times the 4th power of your Kelvin temperature. It's a very, very unusual formula. the fourth power of temperature. You hardly see anything like that in physics that is that sharp. So what that means is if you double the temperature, now this is doubling Kelvin, so it'd be a major, major increase, you get 16-fold increase in the radiation. And so the amount of radiation we emit is quite sensitive to temperature, and that leads to sort of a very precise balance between the incoming radiation we get from the sun and the outgoing radiation that the Earth emits. And fundamentally, this is really the reason, this black body concept is really the thing that determines the temperature, the physical mechanism of the heat loss of the Earth. So we're getting in all this energy from the sun. The majority of it we lose from this black body effect, which is kind of invisible in our daily lives, but we can see it very clearly in thermal imaging. I'll mention one more thing about this, is that the reason we have special cameras for this is because of the wavelength of the light. These photons, electromagnetic waves that we emit because of this atomic jiggling, they're not in the visible spectrum, so we cannot see them. They're in the infrared spectrum, so they're invisible to the human eye. Okay, so we'll come back. So on Monday, we'll have a guest lecture, and then on Wednesday, we'll close off with planetary climates, and then probably some paleoclimate. Okay, have a good weekend, everybody. I'll post the marks tomorrow, and I will see everybody on Monday.